The next type of reactor that we will discuss is called a plug flow reactor, or PFR. PFRs are used when chemical engineers want to concentrate a species of reactant when we're working with positive order kinetics. PFRs are commonly drawn in process flow diagrams as horizontally oriented cylinders, and we have an inlet flow rate, FA naught, and an exit flow rate, FA, where A denotes the reactant or the limiting reagent in a reaction that's occurring. And doing a mole balance on a PFR is challenging because, unlike CSTRs, the continuous stirred tank reactors, and batch stirred tank reactors, BSTRs, the concentration profile of A can vary inside our PFR as a function of length or accumulated volume. So as the molecules of your reactant flow through the PFR, they are reacting, and so we would expect to have a negative trend in our reactant concentration. And this makes things a little bit challenging for us. So to overcome this, what we do is something referred to as a shell balance. And in a shell balance, what we do is we analyze a very thin disk inside our reactor, and then we integrate over the entire reactor. And in this shell balance, if we zoom in on this disk, I will call the initial point V and the ending point V plus delta V. We will have some moles of A coming in at V, and we'll have some moles of A leaving at V plus delta V. And inside this volume element, we have a reaction occurring. Our reactant is being consumed at a rate RA per volume. So we need to multiply this by the volume of our shell, which in this case would be delta V. So the next step in deriving a total mole balance on a PFR is to look to the mole balance equation, which tells us that the accumulation is equal to in minus out plus generation minus consumption. And quick note, generation and consumption are commonly lumped together in RA, and if we are dealing with moles of A being generated, RA will be a positive quantity. If we're dealing with moles of A being reacted, it will have a negative sign in front. And what we will assume is that our plug flow reactor is operating at steady state, so we can cancel out our accumulation term, and we will say that the inlet term, in this case, would be FA evaluated at V, so 0 would be equal to in FA evaluated at V minus out, which is FA leaving at V plus delta V, and then plus the rate of reaction that's occurring inside, which would be RA delta V. And so the next step that we're going to do is we're going to divide this whole equation by delta V, and then take the limit as delta V goes to 0. And so what we notice is that we have a definition of derivative in here. So this term turns into, so 0 is equal to dFA dV, dFA dV plus RA. And there's no delta V here because it canceled out. And so what we end up with is dFA dV is equal to minus RA. And if you wanted to have an idea of what kind of reactor volume of a plug flow reactor you'll need for a desired conversion, we can do that by going back to Stoich tables and realizing that the definition of FA is equal to FA naught times 1 minus x. Therefore, dFA FA is equal to minus FA naught dx, and we can plug this relationship into this equation, and we will say that minus FA naught times dx dv is equal to minus RA. This is a good place to be able to get to because it tells us the relationship between desired conversion X, the required volume of your reactor V, your inlet flow rate, and your rate of reaction. And so what we can do is we can integrate this, and if we do that with respect to V, we find that volume, the required volume of your reactor, is equal to FA naught times the integral from X in to X out, so your inlet conversion minus your outlet conversion, times RA, I'm sorry, it's actually dx divided by RA, and there's a negative sign here, sorry about that. So commonly what we will find in practice is that X in is equal to 0. So if we have no reaction occurring before it's entered the reactor, this term usually equals 0. X out will be the desired conversion. And on a problem or in the real world, what we do next, once we've arrived at this equation, is make the substitution in for minus RA, because RA, your rate of reaction, is a function of conversion. So to get RA as a function of X, we're going to turn to Stoich tables. And once you have derived how RA is a function of X, we can evaluate this integral to get an idea of what kind of volume will be required. I'll give an example of this. Let's say we had reaction A goes to B, so 1 mole of A forms 1 mole of B, and RA minus RA, because it's the rate of consumption, will be equal to K times CA. And we'll just make it clear that it's C sub A. And if this was an all liquid reaction, we can write this as K times CA naught times 1 minus X. And so the next step we would do, now that we have RA as a function of X, would be to plug it into here and evaluate the integral to find what the needed volume of the PFR is. So I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.